Let's look at the following problem. Two masses rests on an inclined plane arrangement as shown below. M2, that's that one, has a mass of 200 grams and rests on M1. The mass of M1 is 65 grams. The coefficient of static friction between the two blocks is 0.5, that is that surface right there. The coefficient of kinetic friction between the lower block and the plane is 0.35, that's that surface. An upward force F that is parallel to the plane, that is this force, is applied to the lower block. Find the acceleration of the lower block, namely mass M1, when the upper block M2 just starts to slip on it. And what is the maximum value of F before this slipping occurs? The best way to begin is by looking at the free body diagrams of the system. Now, you have a couple of masses. You have M2 and you have M1. So you should analyze two free body diagrams, one of M2 and the other one belongs to M1. So let's look at M2. Let's analyze all the forces that are acting directly on M2. The first is the weight of M2 that acts vertically downward, like that. Let's call that W2. And its expression is the mass M2 times gravitational acceleration. The second one is the normal force, like that. So this normal force that's acting on M2 is perpendicular to that surface between M2 and M1, hence the word normal. Note there is static friction along that surface. M2 would tend to slip this way. So that means there is static friction acting that way. Let's call it Fs. And the static friction again acts on the surface between M2 and M1. And then you have this acceleration of the system. And we are told that the system were to have an acceleration A. Because of that force, the acceleration is also upward. So we note one more time, this upward force F acts directly on M1. So it does not enter the free body diagram of M2. As we have seen in our previous videos, this W2 has two components. One component would tend to drag the mass M2 that way, and the other component acts vertically downward, opposing the normal force. Let's call that this component here as W2 parallel. So that is the component of W2 parallel to the plane. And the component of W2 perpendicular to the plane, we can write it as W2 perpendicular. So let's express W2 parallel and W2 perpendicular in terms of W2. W2 is the hypotenuse of that force triangle, so that is W2. W2 parallel is parallel to the plane, so that is W2 parallel, and that is W2 perpendicular, which is that component. So that is the corrected diagram. And the angle between the two components is 90 degrees as expected. Note that this is the angle between the vertical direction and the plane direction. So this is the plane direction and that is the vertical direction. So that and that must be the same angle. But because this is alpha, then this has got to be 90 minus alpha. So this here is 90 minus alpha. That means that is alpha. So what that means is W2 parallel, that is this, over W2 has got to be sine of alpha from this triangle. So that means W2 parallel is quite simply W2 sine alpha. Likewise, W2 perpendicular over W2, so that is this over that, equals cosine alpha, which means W2 perpendicular equals W2 cosine alpha. Now let's proceed with Newton's second law. Let's just look at M2. There is only one forward force, and that is the static friction. So static friction, F sub s, minus the force down the plane. So in this case, there's only one W2 parallel. W2 parallel equals the net force. And the net force, according to Newton's second law, is mass times acceleration. So in this case, M2 times acceleration. We are dealing with a scenario just starts to slip. When M2 just starts to slip on M1, that means this static friction has got to be maximum right at that moment. So let's write it F as maximum, F as M. Now let's substitute for all these terms. The maximum value for the static friction on M2 is given by the coefficient of static friction, which we already know, times that normal force on M2, namely N2. Now, W2 parallel is given by that expression. So W2 is M2G sine alpha. Now from this triangle, from this right angle triangle, the hypotenuse is 13 cm. Because this is 5 cm, that's 12 cm, so that has got to be 13 cm. So sine of alpha is 5 over 13. So let's write that, 5 over 13 equals M2. M2, we know, has a mass of 200 grams. So M2 times A. Note that we know mu sub s is 0.5. N2 can be worked out. M2 is 0.2 kg, and we can determine the A. So let's figure out what N2 is. There is only one force that neutralizes or balances N2. That is W2 parallel, because otherwise M2 would move in that direction, but it doesn't. So this must be the same as that. So N2 equals W2 perpendicular. That is M2G times cosine of alpha. Cosine of alpha from the triangle is 12 over 13. That is this over the hypotenuse. So now we know N2, we know the coefficient of static friction, we know M2, and we can determine the acceleration. When you do the calculation, you'll get the following value for A. Namely, for part A, the acceleration turns out to be 0.754 meter per second squared. Now let's do part B. What is the maximum value of F before this slipping occurs? So let's look at the free body diagram of M1 now. There is one force already been labeled that is acting directly on M1, that is capital F. There is kinetic friction down the plane that is acting directly on M1. Let's call it F sub K. Of course, there is this total weight M1 plus M2, because the weight of M2 is acting on M1. So the total weight here is M2 plus M1 times gravity. And this weight has two components as always. One is the perpendicular component and the other one is the parallel component. And since M1 and M2 is part of the same system, both have the same acceleration A in an upward direction. So let's apply Newton's second law here. The forward force or force up the plane is F. The force down the plane, there are two. One is the kinetic friction and the other one is W parallel. So let's subtract those two from capital F. So F sub K minus W parallel. And this is the net force, and according to Newton's second law, net force equals MA. Now M is the sum, M1 plus M2, times the acceleration that we have actually found in part A. Let's look at the term by term here. What is kinetic friction? Kinetic friction equals the coefficient of kinetic friction times the normal force on M1. And normal force on M1 goes like that. Let's call it N. It opposes this W perpendicular, as we have already seen in the case of M2. So that means it is mu K times W perpendicular. As before, we note that W perpendicular is a W cosine alpha and W parallel equals W sine alpha. It works the same way as we did show for M2. So let's use this equation to calculate the maximum value of f. So f minus f sub k is mu k, which we know to be 0.35, times W perpendicular, which is W times cosine alpha. Cosine alpha from that triangle is 12 over 13. Minus W parallel, which is that, so minus W sine alpha. Sine alpha is 5 over 13. And that equals m1 plus m2, which is just W over g, that is there, and times the acceleration. So we know everything in this line, and we can determine the maximum force. Why this is a maximum force? Because we have, or at least we are making use of the value of A that we have obtained in part A, that value. And that value is calculated when the upper block just starts to slip on the lower block, namely when that static friction on this is maximum. And solving for F, we get the following value, 2.04 Newton. And that solves the problem. Thank you for watching.